Welcome to Engineering the Hard Problems, the podcast where we talk about real engineering challenges hiding under everyday infrastructure. I am your host, Surya Vishwanath, lead software engineer here at Epsilon. Today, we'll talk about loyalty systems. And before you turn off, I promise this is not a product story. Loyalty systems at scale are one of the most densely layered decisioning systems in retail infrastructure. Millions of profiles, millions of transactions, hundreds of business rules per transactions, all of it sitting under payment flow and checkout counter latency. To unpack this, today I have with me Geordin Jose, Senior Director at Program Delivery here at Epsilon. Geordin, welcome to the show.
Thanks, Surya, and I love the framing. The reason why this problem is interesting to engineers is precisely because from outside it looks very trivial. The points goes up, happy customers, but the underlying machinery is quite complex.
So Geordin, let's start with a question that most engineers would get wrong. Someone handed you a loyalty spec, the naive read would be to set up your profile, set up your eligibility rules, and issue your points. A database problem. What am I getting wrong?
Almost everything, because the database is the easiest part. The hard part is the real transaction and the decisioning that happens on every transaction that needs to be accurate, personalized, and need to return within milliseconds because it's in the checkout flow. There is a real customer waiting at the register. There is a POS system that's waiting for a response, and you don't get to be slow there.
Yes, you're right. Unlike a payment failure which has defined fallback path, customer doesn't view the loyalty system the same way. A loyalty failure is invisible and immediate.
That's true. Customers doesn't think it's a system error. They feel like I didn't get my point, I didn't get my offer, so this brand lied to me. That's a different level of damage.
So latency and accuracy are equally hard trade-offs, not a constraint.
Exactly, and these actually compound on three different factors, right? One is the rule complexity. It looks like hundreds of rules, like an if-else chain, but actually they are not independent. They overlap, they conflict, they have their own priority hierarchies. So a customer can earn a base rule, they can get a promotional offer, they can also get a tier multiplier, and a combination of all the three where a fourth edge case comes out when nobody would have imagined when they set up this rule. So you're not actually evaluating a list, you're actually traversing a decision graph at runtime. Secondly, the latency. You cannot really force the graph on every transaction. So you are constantly competing between completeness and speed. And that balance between these two, you need to get almost on the 99th percentile. The third one is the distributed consistency problem. So loyalty systems generally work with payment infrastructure, retail systems, customers' mobile app, web applications, even the underlying loyalty system simultaneously. And you need to keep consistency of data across all of this all the time. Even a small failure can become wrong offers to customers, missing points, or even over rewarding customers, which is actually a financial liability for the brand. And all of this to happen at times on a PCA level security infrastructure.
So that's a genuinely hard systems problem, not a CRUD app with a loyalty skin on top. You've got accuracy, compliance, consistency, and latency, all as equally hard constraints all at once. What are some of the key architectural decisions? Could you please walk me through them? What do teams get wrong?
Yeah, in my opinion, there are really three key trade-offs that someone cannot avoid. That is, anybody who is building at this scale need to have a careful thought process through all of these. The first one is real-time versus pre-compute. Real-time is accurate, but it is expensive. If you try to pre-compute everything, which is faster, but it is stale. So by the time your transaction fires, the points would have changed, or even the customer threshold would have changed.
Very true. What I remember was that we ended up with a hybrid system. We pre-compute our eligibility rules and use the real-time systems for accuracy.
Yeah, That's a good way to look at it, but the problem there is, again, you need to keep the real time as well as the pre-compute layers in sync, and that in itself is a distributed system problem. But I love the idea of keeping it hybrid, so you are actually trading one hard problem with a different that is more manageable. So the second decision that I would imagine is about stateful versus stateless.
Stateless is beautiful, horizontally scalable. But loyalty systems are inherently stateful. Customer information, transaction history, points earned, none of this is momentary. I think the answer is to have it in fast access layers, caching, or specific data stores.
Yeah, that way you can keep it stateless to a way, but still access the state whenever you want, evaluate and respond. In that way, you're also keeping the separation of concerns between the stateful and stateless boundary. And the third trade-off that I talk about is real-time versus batching. Not everything need to be executed at real time, like tier evaluation logic or annual tier spend, etc. That can be very async batch jobs, but real-time decisions, that has to be through some API streaming so that you keep low latency. You are not waiting for any batch job to run, etc.
I think that's where some of the teams get it wrong. They make things that need to be real time batch and end up with angry customers, or change things that need to be batch into real time and end up destroying their cost model.
That's right. I think that's the experience talking. So that's where the engineers need to know where to draw the boundary and also stick to that, even when your underlying platform or products push you back. Just make it very clear what needs to be worked in a batch versus a real time. And that's a significant part of the job.
There's a perception that I hear from teams outside of loyalty delivery that a mature system like Epsilon's abstracts most of this away. How accurate is that?
It's partially accurate because if I think about Epsilon's People Cloud loyalty as a platform, the platform kind of takes most of the load with respect to the decision infrastructure. It's very powerful, very flexible for different industries and vertical needs. But every customer brings their own requirements. They have specific security needs, compliance requirements. They also have different integration patterns with their existing stack, etc. That needs to be modified. It's not EPCL is made out of the box to work in that way. So there is real engineering. It's not just configuration in that case. I can give you a concrete example, which we did recently, data tokenization, which is not a loyalty feature if you look at, right? But when you work with financial and payment clients, you deal with a lot of PII, payment card information under PCI constraints. Now, either client builds it or they might ask you to do it. In this example, our delivery team started building a full tokenization stack so that we keep the payment information away from the loyalty systems. And that's not configuration, that's real engineering skills.
So the platform is the foundation, and delivery engineering is building what that client needs for their industry under these constraints.
That's it. I generally use this analogy of a car. The platform is the engine, delivery is the one who builds the vehicle, and the vehicle ride on the road that very specific customer needs and they drive on. So that's the engineering challenge. So everything needs to come together really well. If anybody is telling you that loyalty is a configuration, either they haven't delivered in that scale, or maybe they are so lucky with their clients, they are riding on a really smooth road.
Let's stay on a security thread. PCI compliance, PII, and financial data. Latency at this scale must be a nightmare. How do you architect security without it becoming the bottleneck?
The core principle is security has to be a layer from day one. It cannot be bolted on top thereafter. If you do it after, you either break performance or you make some gaps, and both are bad. So in the specific example that I talk about in tokenization, we use layered AWS architecture. At the perimeter, it's a WAF that kind of filters malicious requests to come in. Then you have the API gateways to kind of handle the throttling at runtime. If you come to the compute stage, you have ECS or EKS as containerized services. You have Lambda as lightweight microservices and run the async jobs, etc. You have the security manager that take care of the keys. So if you look at tokenization is a must pass through layer that sits even before any request comes into the loyalty platform. That way we kind of keep the malicious content out. We also not allow anything that to come inside the loyalty platform that is unnecessary.
So your observability is again built with AWS services like CloudWatch, distributed tracing, and logging.
Yeah, that's right. I mean, you can't really secure anything that you can't see. So observability is a key there. Even performance, Redis style caching, event-driven pipelines, etc. That kind of keep your latency under control, even with the security overhead.
So you're talking about security as an architecture, not an audit.
Yeah, obviously, I think security audit is not as interesting for engineers as security architecture. But if you hold a line to that architecture, the auditing becomes very easy.
So in this example of tokenization, security has become an enabler for you. But with all of this, things can still go wrong. How do you design for this?
The basic assumption is things will definitely fail, and that is not a pessimism. That's the distributed system reality at this scale. So the question is never how do you build a system that never fails. It's about what happens when a failure occurs and how the different components behaves to that failure.
So you're talking about graceful degradation.
Yeah,
When a system goes down, when your rules engine goes down, your system would revert to a baseline offer and try and prevent cascading failures.
that's right. Even like transient errors, how do we retry those errors and kind of stop the retry storms, etc. And on top of all of this, observability that lets you to see everything real time. So when something goes wrong, you should know within seconds where and why, so that you can apply a solution to that. So you can't wait for your log aggregations to run and then prevent that issue. So that's very important. And these days, it's an interesting conversation of intelligent observability. Even with AI, there are a lot more advanced observability options.
What about testing? I imagine unit testing these individual rules is the easy part.
Frankly speaking, unit testing is irrelevant today. What I mean is, mostly all of that can be automated. Let me ask you this question. In your experience, what goes wrong in production?
You're right. Rule stacking in ways that no one really imagined, that's something that tends to go wrong in production.
Exactly. So that's not something that you can stop with unit testing. To just expand what you just said, there are multiple rules that individually works correct, but combined might give a wrong outcome. Now, if you have to figure that out, you need a production like environment, which is mirrored real time, your transaction, similarly how it happens in production. And you kind of replay all of this whenever there is a new rule comes. That's the only way that you can find such failures. If you don't do it, you're actually QAing in production.
Yeah, so resilience, testing, and observability, all of this lies under your checkout payment flow.
Yeah. So you can't make anybody wait there. So you can never tell a customer, wait for it. I have built a robust system, secure system, but if it's kind of making any customer wait more than 90 seconds at a checkout counter, it's failed. That's it.
You spoke about AI. Can you give me how this sort of works in your system? And I want the real answer, not the press release version.
Yeah, the today no conversation stops without AI, right? So the real answer is AI helps where the static rules hit the ceiling, like hyper personalization, for example.
You mean hyper personalization using an ML sort of fitting rules into your customers based on their spend habits or transaction habits?
Yeah, I mean, put it this way. If we are able to kind of predict and act on such signals that you mentioned, for example, this specific customer buying at this specific time right now is kind of responding to this offer. And if you can give that signal, the cross sell upsell opportunities for that brand is like tremendous. The other area that I can think about, or I call it as intent aware systems, right? Why is this customer buying at this point in time in this channel? What is his current need? What can brand get from that kind of an information, right? So what kind of offer can be put in that specific time for that customer? So if you are able to understand the intent of your customer, it's way beyond loyalty points and offers. It's actually, again, what I said, it's supporting your cross sell and upsell in a big way.
Sure, you also spoke about AI investment into observability systems.
Oh, yeah. So I call it as intelligent observability. Today, if you look at uh, our observability systems are working on what has happened in the past or some events that kind of already executed. With AI, we can even predict what is going to go wrong. So you can look at the anomaly signals that are coming in and try to predict when something might go wrong. And even if it goes wrong, you can initiate an autonomous recovery playbook or protocol that kind of prevent the damage. So that's the level of observability that we are talking.
The resilience that you spoke about is exactly what AI needs to work in this system. The foundations that you've already built it on is what AI requires to work.
That's true. That's an interesting thing because today everyone try to put some ML AI model on top of their legacy stack and kind of choke their system. But actually, you need a real business case. You need to solve that business problem first, even before thinking to put an AI model on it. So the architecture that we build and the ML models and infrastructure available has a lot in common. Until you come very close to each other, the AI investments are not worth. But if you are able to do that, it's so beautiful to see how AI can give you results.
This is exactly the kind of conversation I wanted to have, Jordan. Thank you for taking something that looks mundane from the outside, a loyalty program, and show us how it looks like to actually deliver it at this scale. Distributed consistency, resilience by design, security as architecture. These are things that you have to build in at your architecture level and decision making.
That's right. And thanks for asking the right question, Surya. I hope genuinely this gives the engineers a sense of what it takes to build such systems at scale. And if the problem is interesting for them, I'm very sure genuinely there is a lot of hard work to be done here.
Thank you, Jordan. That's it for this episode of Engineering the Hard Problems. Please share this with an engineer who might find it useful and thinks distributed systems only live in streaming services and search engine. We'll see you at the next episode.